Hello, my name is Arshia Elahi, and today I'm going to be discussing my critique of the DropConnect research paper. So the full title of this paper is Regularization of Neural Networks Using DropConnect. The authors of this paper are Li Wan, Matthew Zahler, Sixin Zhang, Yan LeCun, and Rob Fergus. This assignment is for the CS4375 course, and it's created on this date. So, just to give an introduction, this paper was published in 2013 by AI researchers at NYU or New York University. And this paper details DropConnect, which is presented as a potential substitute for dropout to reduce overfitting. And what dropout is, it's basically a method to reduce overfitting by introducing sparsity. And in normal dropout, a randomly selected subset of activations in each layer of a neural network are set to 0. However, DropConnect comes and sets a randomly selected subset of weights within the network to 0. So it's an alternative to traditional dropout. So before we go on to the methods and the testing, I first wanted to discuss the credibility of this paper. It was featured on Google Scholar with 2,237 citations. It was published in Proceedings of the 38th International Conference on Machine Learning, which is a very reputable and prestigious conference. And the organization of these authors is NYU, which is a respected university for their computer science research, especially in AI. And finally, this paper was written fairly recently, being written in 2013. And this implies that this article, is up to date. It included recent information. So we first need to discuss neural networks. Neural networks are a series of algorithms that seek to identify relationships in a data set. Now, these can be used, for example, for predictions and for classifications. So if we look here at this neural network architecture, we see that there are certain inputs that come from previous layers, or if in the case of the first layer, the training set. And then there's a layer of weights, and then there's the summation and bias, which is the result of adding to a bias to the sum of all the weights multiplied by their inputs. And then finally, this is put into an activation function, which occurs here. And then the function, which is the activation, ends up having an output. And that's what's passed on to future layer or future parts or future neurons. And those eventually lead to a prediction. So looking back here, we see that we're essentially multiplying weight 1 by the first input, otherwise known as x1. Now, a neuron can have multiple inputs. So we can assign a weight to each of these inputs, which kind of represents the strength of the connection. And then, of course, there can be a bias added to it. And then the activation function takes all of this and results in an output. So a big problem with complex machine learning models, such as neural networks, is that they are very susceptible to overfitting. What overfitting is essentially where the model fits to the training data set well, but performs poorly on data sets it hasn't encountered before. Otherwise, it has a high testing error. And the reason for this is because the model overfits to the training set, and as a result, it performs poorly when it encounters data it hasn't met before. So this image right here is a very great example of this. We can see that these black dots are the initial training set, and it appears to be fairly linear. So a linear model would appear to do well for this type of data. However, what the model is this very complex, and as opposed to just being a linear function, it's some kind of polynomial function that tries to get all of these points together. So it's overfitting to the training set. If I came and put a point here, I don't think that this could be able to predict that point well. There would be a large gap or a large error. And again, this is the result of the model being overly complex and overfitting the training data set. So there are certain methods that exist that reduce overfitting. The first thing we can do is we can input more training data to increase exposure. Basically, when the model is exposed to a larger range of data, if if there is a new data set, it can probably fit to it a little bit better because it's gained more exposure with the data. And the simple solution here is, again, just to input more training data. Or sometimes what's done is, like, for example, an image is flipped, an image is rotated, some inversions occur in that image, and you're basically taking a single image and making multiple different variations of that and treating it as data. So another way to reduce overfitting is by reducing complexity. And this is done by removing layers or reducing the number of elements in a hidden layer. And this is basically what a dropout layer does. It's a little bit of a more advanced version of this. And then regularization can also be applied to the cost function. And there's L1 and L2 regularization. So what dropout layers do is that they randomly remove certain features by setting the activations to 0. And this introduces complexity by reducing complexity at random, removing certain elements in the layers. So just to discuss weights and activations, in neural networks, weights are parameters that transform the input through multiplication. And they're going to represent the strength of the connection between two units, whereas an activation function of a node defines the node's output by putting the results of weight plus bias, so the sum of the weights times the inputs plus the bias, those are end up being put in the function. So as we can see here, f is our activation function, b here is our bias, and then here are our weights, which are multiplied by our inputs. So the general function that was highlighted in the paper is r equals a of u, where u is represented by wv. Now here, a is the activation function, w is the weight matrix, and v is the input matrix. So to show where dropout affects and where DropConnect affects, we again need to know that dropout randomly sets the activations to 0, whereas DropConnect randomly sets weights to 0. So dropout here is only affecting this function, this activation function, whereas DropConnect, which is the method that the researchers are advocating for, it randomly sets these weights to 0. So here r equals a of u. It's been color coded. So a represents the activation, shown in red, and u, which is blue, represents basically the weights, because wv ends up becoming u here. And so there is obviously a role of probability in dropout and DropConnect. So in dropout, each element of a layer's output is kept with the probability p. Otherwise, it's set to 0 with a probability of 1 minus p. So DropConnect is actually a generalization of dropout in which each connection, rather than the output unit, can be dropped with this probability 1 minus p. And this, as we can observe, follows a Bernoulli distribution. And there is a Mr. Bernoulli over there. So how is this actually done? It's done through a linear algebra concept called masking, where if we look at dropout, the formula here is r equals m matrix multiplication a of wv. M here is going to act as a binary mask vector with a size of d, with each of its elements, j, being drawn independently from a Bernoulli distribution, mj. And DropConnect's different from that. Instead of the mask occurring here multiplied by the activation function, it's going to actually occur inside the activation function. So we can see here. Now this again is occurring in like 3 parts. There's this part, and this part. And then M is a binary matrix encoding the connection information and is taken from the Bernoulli M of ij. So just to show an example of this, here's our matrix A, here's our matrix B, and then this is our output by multiplying these two. So if the matrix A is all zeros, well, here, let's look at this. AE plus BJ would be the same, or BG would be the element that is occurring here in the first position. So all we would have to do to set this equal to 0 is A and B would have to be 0, because if they are, it doesn't matter what E or G is. when you multiply a number by 0, it's just going to be 0. So from this, if the matrix A is all zeros, then this is acting like a full mask. It's setting the output equal to 0, no matter what these values are. And this is going to be done at randomly. A could be 0, B could be 0, multiple of them could be 0, and this is going to follow a Bernoulli distribution. So in order to, so here's the neural network architecture. We can see here that DropConnect appears way less structured than an effective dropout. And this is going to imply more sparsity, which is actually good. It's what we want. The more disorderly this is here, the better it is for the purposes of our testing and doing its job at reducing overfitting by reducing complexity. Now, as we can see here, DropConnect and Dropout are different in the architecture. So the normal architecture with a dropout layer would involve the input, the features, an extractor would go here, and then this DropConnect layer wouldn't actually be here. Instead, a dropout layer that's similar to this would occur right after the activation function. And then that would go into a softmax layer and be used for a prediction. So DropConnect is different. Instead of having a dropout layer occur here, it's having it occur all the way back here. So that's the big difference. Now, these researchers actually wanted to implement and test this. So they used the CUDA ConvNet package and developed a custom GPU kernel. And this was done in the Python language. Then they created instances of a mask for the weight matrix, which would be randomly generated. Then they created a fully connected layer and softmax layers, and they had different activations like ReLU, TANH, sigmoid, etc. Then they trained various data sets using the mini-batch approach for inputs. And then they recorded their results by comparing performance, otherwise the testing error or accuracy in neural networks with the dropout layers and the DropConnect layers. And this was done using like a confusion matrix, the actual accuracy measurement. Okay, so for actual testing, their claim was that DropConnect results in higher testing accuracy than dropout. The procedure here involved training 5 independent networks with random permutations of the training set. Then they would train the fully connected layer using dropout, DropConnect, or neither. Neither is going to act as the control. It's basically where no dropping is used. And then at inference times, they would draw samples and average their activations. Then they calculated the testing error rates to determine the overall performance. And then they experimented the above process with different activation functions and different prediction topics. Such as MNIST, CFAR10, etc. And I'm going to explain each of these. So very quickly, okay. Sorry about that. Okay, so MNIST is basically the handwritten classification task where, for example, if I write a digit 3 with pen and paper and a camera like scans it, can it predict or classify what I have drawn? So is the 3 that I hand wrote going to be classified as a 3 by the neural network? And here the results show that the DropConnect method had a lower error rate than dropout and the control, which was no dropping, in the MNIST experiment for ReLU and TANH activation functions. However, it had a slightly higher error rate for the sigmoid activation function. As we can see here, for the ReLU and the TANH, the voting error to basically say, okay, what's the classification of this particular handwritten digit? It was lower than both the no drop and the dropout, the no drop being the control. And it was actually statistically significant as well. We can see that the error rates, once added or subtracted, they're still different from each other. So it's statistically significant. Whereas also in the TANH or in the sigmoid, it was slightly, it had a slightly higher voting error than dropout. However, it was still performing better than the no drop. And this classification error rate was done with 2 fully connected layers having 800 neurons each, and no data augmentation was done in the experiment. And this is taken from the research paper. So as for the CFAR10 SVH, okay, so back to the presentation. So this was also done for the CFAR10, the SVHN, and the NORB experiments. And CFAR10 represents an image classification problem done with different colors. SVHN is the street view house numbers problem, and NORB is related to object classification. And in all of these, a convolutional neural network is utilized. So in the CFAR10 testing, the DropConnect had the lowest error rate, otherwise known as the highest performance, having an 18.7% error rate compared to 19.7% error rate for dropout, and a 23.5% error rate for no drop, which was the control. So it outperformed dropout and no drop. And then in the street view house numbers test, DropConnect again had the lowest error rate. In the NORB experiment, DropConnect had a higher error rate than dropout, although it was still lower than the no drop. So it had a rate of 3.23%, where dropout had 3.03%, although again, it was still lower than the control, which was sitting at 3.36%. So the overall results showed that DropConnect often outperformed dropout and always outperformed the no drop control. This result was statistically significant as well. DropConnect allows more control and is able to introduce greater sparsity, as we saw in the previous one of the previous slides showing the different structures of the masks, with the DropConnect method being much more sparse. So overall, the goal of these researchers was met, and their claim was verified empirically based on the better performance of DropConnect. And here it should be outperformed dropout. So please consider that. And as we can see with these graphs, dropout appears to at the beginning with lower hidden units, it performs not very well, but as the number of hidden units increase and the model becomes more and more complex, it basically results in a lower testing error. And this is very significant because it appears to be decreasing the error rate at a higher rate than with the DropConnect. And this is really great for more complex models. And again, as we see here, they all seem to follow a similar trend when it comes to percent of elements kept and the testing error, and the cross entropy is essentially lower for dropout than DropConnect. Okay, so in summary, this research paper introduced and explained DropConnect, which was an alternative to dropout that introduces sparsity and reduces complexity by setting the weights rather than the activations randomly to 0, and it's used to reduce overfitting. The researchers implemented DropConnect through building a full neural network, training it, and experimenting with different methods for dropout layers. And overall results showed that DropConnect outperformed dropout, having the highest accuracy rate / lowest testing error rate. That should be testing. And DropConnect, as a result, can be used as an alternative to dropout, helping reduce overfitting more effectively, making it applicable in many machine learning applications. So some of the critiques of this paper, these being the positives from this paper, is that it was very informative and easy to understand, even for a student like me who's still learning about this. And it was very great that it provided these relevant formulas and explained all of the variables and details, the main one being the output function. And it included many visuals, including tables and the model of the neural network architecture, so that the viewer could actually see the difference in sparsity. Furthermore, it was very procedural in terms of the formatting of the implementation and testing. So by being procedural, it helped someone who's trying to replicate this experiment follow it a little bit better. It was organized into multiple sections and subsections, which were very easy to digest. And in terms of actual data, I loved how it included multiple trials and experimentation involving various ML problems. For example, the CFAR 10 is very different than the normal handwritten classification. So it's really great that it used these methods in various machine learning applications as opposed to just focusing on one or two. So we could see the results over many experiments. And it was also really amazing that they included a control group with statistics. So the control group was also mentioned because that's very important. Since the variables need to end up, or the different methods end up being needed to be compared to like a control group. And it had a lot of statistics that were used to prove statistical significance, the error rates and the error, like basically an addition or subtraction of an error. And that would be like the error bar. And it also it was very great that it discussed limitations and some issues with DropConnect, such as some memory issues, but it also included how they were solved, such as through mini batches and other techniques. And it finally had frequent use of evidence to back its claims. Every claim it made in the paper, it explained why this was the case through empirical evidence. Now, there were a few very minor negatives I had with this research paper. So one of the most minor ones was that data could have been represented with bar graphs rather than tables, because bar graphs essentially help visualize the data better, and it could have included error bars, because back on this slide, what I had to end up doing was adding and subtracting the error to see if it was statistically significant myself, whereas a graph could do this more effectively as like a visual representation. So, going back here. With error bars, it could show that if they overlapped, then it wasn't statistically significant, and if there was like a difference, the error bars didn't overlap, then it was statistically significant, and that would help just the viewer see that a little bit better. So this is something like they could have done. This is one of my personal projects that actually involved some AI, and here I've shown a bar graph, and here I have these error bars. So for example, for zero calibrations, the control and the traditional hearing aid, their error bars overlap. So these are not statistically different from one another. Whereas the engineered hearing aid, the error bar does not overlap with these two. So it is statistically different. As we can see here, and here, all of these appear to be statistically significantly different from one another. No error bar overlap. And this is something that they could have done. So furthermore, I think that some Python code could have increased the replicability of the experiment. It was mostly done in like pseudocode, and it only covered certain parts. Some more code and more inclusion of like what packages they utilized. It would have helped increase the replicability, but this is a very minor issue. And finally, I think that the conclusion could have been longer to emphasize the impact a little bit more. They really came up with a really great idea for reducing overfitting, and some more emphasis on the impact it could make would really help. So my biggest issue with this was that there was no discussion of a possible combination of dropout and DropConnect. The thing is, dropout and DropConnect should not be mutually exclusive. For example, I can I can mask some of the activations, and I can mask some of the weights. It is completely possible to do both of these. So dropout is only affecting the activations, which as DropConnect is only affecting the weights. In theory, both of these could be done together and could possibly even reduce overfitting a little bit better. And again, this could have been a very good future application that they could have discussed. Now, the likely reason they didn't include this is because their entire goal was to say DropConnect is a better alternative to regular DropConnect is a better alternative to normal Dropout, although I think a discussion of using both of these together would have been very appreciated and a very interesting idea. So, in conclusion, this research paper was extremely understandable and informative. It emphasized with empirical evidence the use of DropConnect over Dropout for reducing overfitting. It was very convincing in regards to this argument, and it was also very easy for even someone with basic experience like myself to understand. And the goal of DropConnect, again, was to focus on randomly setting weights to zero rather than activations, which introduced controlled sparsity and simplification of the model. Furthermore, DropConnect outperformed Dropout in the control, no dropping in most of the testing. So this verified the researcher's claim. Now, I had a few negative critiques of this paper, but they were very minor, involving some like formatting, potential use of bar graphs, inclusion of code, and finally the lack of discussion for both for an application using both Dropout and DropConnect. But overall, this paper and the DropConnect technique are very impactful to machine learning research and applications, and this paper was very well written and a very enjoyable and informative experience for me. And that's the conclusion.